to this series of lectures on marine hydrodynamics under the NPTEL program. In the last class, we are talking about wave energy relations and wave scattering. Today, we will continue the same. When there is in a channel, in fact, towards the end of the lecture, I started this, but I will repeat this again. Suppose I consider a channel of width b and then suppose there is a abrupt change in the channel width. This is, and then this occurs, and initially the width of the channel was b1 and then the width of the channel becomes b2. This is basically the plan view. And then if it is look at the elevation, suppose the depth was h, initially the depth was h1 and after some time let me say the depth has become h2. From depth h1 to depth h2 it moves, wave propagate, and so there is I just say wave scattering due to abrupt change in abrupt change in channel geometry. Change in channel geometry. So, initially the breadth was b1 and I say that just let it let all this takes place at x is equal to 0 on the axis, the real axis. This is the plan view, this is the surface elevation. This position is called x is equal to 0. Here also this line is, this is x is equal to 0. And this I call region 1, this is region 2. Similarly, this is the same region 1, this is region 2. This is my x axis, this is the free surface elevation. So, what will happen when the wave propagate from a depth? There are two things when a wave propagate from this side. So, because there is abrupt change in the geometry here at x is equal to 0, so part of the wave will be reflected, a part will be transmitted to the other side. So, in that case what will happen? I will say that at the interface at x is equal to 0. So, I have two things here. If I just say that I have at x is equal to 0, if you look at for where the changes occur in geometry takes place. If I just say, then what will happen? So, then my at the far field, when because at the ear far away from the channel where the changes occurs, then what will happen to my eta? This will be a combination f's like eta I plus eta r as x tends to minus infinity, and eta f's like eta t as x tends to infinity. And what will happen to eta I? Eta I will be of this form. If I say eta I is a I, let it be anything cos k x minus omega t, and my eta r is a r cos k x plus omega t, and then my eta. You can take this exponential form, but any form is okay, a t cos k x minus omega t. So, this is the form eta I, eta r, eta t. Now, if I look at the again to analyze this problem, if I look at the energy relation, from the energy relation what will happen? I have E b c g, because I have a here it is a this is equal to constant, because in this case this channel is up, this is from conservation of energy flux. and here I have. So, if I look at the left hand as near x tends to infinity, plus minus infinity, I can always say that if I follow this principle of this I call star near x tends to plus minus infinity, I always can say E I, B I, C G I, E I, B I, C G I, this is equal to same as E R, B R, C G R plus E T, B T, C G T. So, basically this is all these terms are associated with the wave incident wave, this is associated with the reflected wave, this is associated with the transmitted wave. So, if I follow this approach, and here if I look at the incident wave, this incident wave is the incoming wave, because this is approaching towards the structure, whereas the reflected wave and the transmitted wave, they are the outgoing waves. So, whatever wave comes in, if this is the place where the waves the changes take place. So, whatever wave that is coming in, the same amount of energy is also, because the energy that is entering approaching towards the location where the changes are taking place, geometrical changes, from the same place the same amount of energy will be radiated, particularly it will be outgoing. So, because of that, this is same as the incident wave energy is same as the reflected and transmitted wave energy. If this is the case, then if I further simplify, E is rho g A I square by 4. So, and that will give me then B I into C G I is C C n is equal to C I n I is equal to E R is rho g A R square by 4 into this side the depth is B I is same as B R. So, this is I am using the notation B 1. So, this will be B 1 and this will be again B 1 plus this will be rho g again A T square by 4 into by 4 into C G G again into C I n I because C G again it will be B 2 into C T n T, and this if rho g by 4 will cancel, this term will get cancelled, then you will get it A I square A y square minus A R square into B 1 C 1 n 1 is same as A T square B 2 C 2 n 2. This is what happens. And what is C? C is nothing but omega by k. So, if C is omega by k, or if I A I square minus A R square equal to B 2 C 2 n 2 by B 1 C 1 n 1 into A T square, which can be simplified further A, if I call it 1 minus K R square, that will be B 2 C 2 n 2 by B 1 C 1 n 1 into K T square. So, this becomes the most general form of the energy relation when there is a change in the apparatus. So, this also can be written in another simplified manner, particularly if the wave is a. So, we have 1 minus K R square is equal to, I can further simplify, because if I write it C is omega by k, or in terms of lambda I can write it, this is B 2. So, B 2 C 2 n 2 by B 1 C 1 n 1 into kt square. So, two things happens if I have, in the wave case I will just consider case 2 case 1. In the case of case 1, okay, in case of case 1, if I just say that my B 1 is B 2, then what will happen, this is same as 1 minus k r square, 1 minus k r square is equal to C 2 n 2 by C 1 n 1 into k t square. And also further, again I will come to this a little later, rather this case. Another thing I will discuss it here, that what will happen near the free surface, near the location that is at x is equal to 0, at the near the fluid, the pressure continuity, thus displacement, the pressure is continuous, the pressure is continuous in the flow, and because at x is equal to 0, the near the location the pressure is continuous, that will give me P 1 is P 2, because the dynamic pressure will be continuous, and once P 1 is P 2, that will give me that eta, because P is that will give me eta 1 plus eta I plus eta r will give me eta t. So, basically we assume that as if the surface displacement is continuous at this point, because pressure is continuous, there is no changes in the pressure takes place there at the interface and near the location. So, that will give me eta I plus eta r. If eta I plus eta r, if I look at the amplitude of this at x is equal to 0, and x is equal to 0, this is at x is equal to 0, and that gives me a I plus a r is a t, and once this is, that means 1 plus k r is k t. So, we have already got another relation, that is from A and this is B. So, from A and B I can always get 1 minus k r, because if I divide it by 1 plus k r, I will get it 1 minus k r is B 2 C 2 n 2 by B 1 C 1 n 1 into k t. Now, if I have k r and k t are two unknowns, this is C. If k r k t are two unknown and I have two equations, so this will give me, what will give me my k r and k t, my k r will be, so this will give me, if I just add this string to add and subtract these two things, I will get my k r is can easily get k r is n 1 C 1 B 1 minus n 2 C 2 B 2 by n 1 C 1 B 1 plus n 2 C 2 B 2, and similarly we will get k t. If we will do that, we will get k t is 2 times n 1 C 1 B 1 by again n 1 C 1 B 1 plus n 2 C 2 B 2. In fact, this is the general relation for the reflection and transmission coefficient when there is a abrupt change in geometry. We can consider several cases, like suppose the case 1, if I say, if it is a deep water, let us say deep water. If it is a deep water case, then we have C 1 is C by 2 and again is equal to same as C 2, and in that case we will have, what will happen, so that will give me n 1 C 1 is C g is rather C g is C by 2, and that will be n 1 C 1 is same as n 2 C 2, and in that case this will give me my k r is B 1 minus B 2 B1 minus B2 by B1 plus B2, and here Kt will be 2 B1 by B1 plus B2. This is simple, and that is the way. So, it all depends on the width, ocean width, because if the in the deep water just abrupt change, particularly this happen in a bay, sudden if there is a sudden change in the width of the bay, then the reflection and the wave will get reflected, and this is the way the reflection and transmission coefficient can be obtained. Another case, let us say case 2. Here this side it is 2 B1, because what will happen when the wave is reflected, it is physically it says that as if the, because one incident wave, one reflected wave, when they superpose, perhaps a standing wave is generated, that standing wave amplitude becomes this becomes this, and as we have seen in my previous lecture that standing waves will be generated once the two waves superpose each other. Now, if we will go to case 2, that is shallow water. If I say shallow water, then what will happen? By n1 C1 is a C, Cj is a C, we have Cj is a C, that is root Gh, and which gives my Kr is H1 B1 root H1 B1, because from here I will get minus H2 B2 divided by H2 B2, and this Kt becomes twice H1 B1 root H1 B1 by H1 root B1 plus H2 root B2. So, then this becomes my reflection and transmission coefficient, and again if we say that B1 is same as B2, this is what we have earlier obtained, that will give us root H1 minus root H2 by root H1 plus root H2, and here is Z2 K2 will be 2 root H1 by H1 root plus H2 root, sorry. So, this is the way in case of deep water and shallow water. In a similar manner, we can see that when it moves from shallow water, deep water to shallow water, the similar situation will occur. Now, here what we have done in this relation, we have done that there is a change in the both in change in water depth as well as the width. What will happen? And here we have used two things, one is the continuity of pressure, as well as the conservation of energy flux. This we have used in this case. On the other hand, the same can be obtained, same long wave reflection, if I just say that we can proceed in the same way by assuming that conservation of mass and continuity of pressure at the interface. So, what will happen in case of conservation of mass? Here we have P1 is P2, and that was giving us eta 1 plus eta I plus eta r is eta t. On the other hand, if we from this is from the pressure continuity, and if you look at conservation of mass, that will give us H1, that will give us H1 B1 eta 1 x is H2 B2 eta 2 x, and this eta 1 x is the overall the depth of water in the left side. This is eta 1 is nothing but my eta 1 will be eta I plus eta r, and eta 2 will be eta t, and basically here we will look into this will happen at x is equal to 0, because the same mass will be mass of fluid, because there is a reflection. So, whatever amount of mass is on the left side, same amount of mass will also is on the right side. So, at this point the amount of mass that will enter this side and same amount of mass, because the total mass at this interface will be the same, whether the wave is reflected, which is transmitted, or it goes to this side. If you look at this side, the total mass will be same, where there is a change in the water depth. And if you look at this also, then also we can easily see that we will again arrive at the same set of Kr and Kt. I am not going to this part, but it can be easily derived. With this I will rather with this part I will the wave transformation I will complete, and I will now go to another thing, what I call the equation of the wave load calculation on a structure. Particularly the second part of this lecture will be wave forces on offshore structure. And when we look at offshore structure, particularly these are large structures, there are the main there are various types of offshore structure, that is gravity platforms, or oil rig, exploration of oil from the activities from the seabed, and other activities. We have various gravity platform, jacket platform, and many others. Even if Arctic structures, we sometimes call this semi-submersible, Arctic structures. These are some of the examples of offshore structure. So, these offshore structures, there are two kinds of things. They are sometimes there are these some large structures, there they have a pile foundation, and particularly pile foundation. So, large number of piles, thin pipes are there, and on which the structure is based, and sometimes they are gravity. In case of particularly gravity based structure, the structures are huge and they may be cylindrical. The structures, these piles can be cylindrical, they can be rectangular, they can be triangular piles, and then, but in case of a huge structures like a gravity platform, the structural size is very large. Particularly if you look at a circular structure, basically cylinder type structures which are extended from the sea surface till the bottom, they are huge in. So, there are three types of so basically to calculate the wave load on these structures, because as I say, this is the size varies, size of the structure varies. When I say look at the size, I always look at the diameter, because the most of the size of the structure varies, because when I look at the diameter, I always mean the, when I look at the size of the structure, I always mean the diameter here, because or the radius of the structure, because the structures, all the structures I am talking about here today, is they are all extended from this free surface to the till the bottom seabed. So, there are to calculate wave load, normally we apply three types of depending on the size and characteristics of the wave. We always concentrate on three types of three methods for calculating the. One is Mauritian equation, one is Krylov theory, the other one is diffraction theory. Although I will not go to the details of this thing, but I will just give a just a glimpse about these equations or these theories, just at a glimpse. I will not go to much detail. And then what happened when you look at the Mauritian equation? This is based on the assumption that there are two components, one is the drag force, one is the inertia force. There are two terms in this, and particularly this is more suitable when the structural size d by lambda is less than 0.2. Here the linear, it is a superposition of two components, one is the drag force part, one is the inertia force part, and they are, in fact this was this on the other hand, if I look at the Proud-Krylov theory, and this is an empirical formula. Which depends on the mass coefficient, there is a inertia coefficient and there is a drag coefficient, and there is a mass coefficient, sometimes we call it the added mass coefficient. On the other hand, when it comes to when the drag force is negligible, whereas the inertia force is dominating, is large. So, then and also the structural size g by lambda is similar to less than 0.2. Then in this case, what we do? Then in this case we apply the Proud-Krylov theory. One of the advantage of this, this is in fact many simple problems can be handled by this, but here it utilizes the, what it does, it utilizes the incident V potential and the corresponding incident potential pressure. Basically, it considers the incident wave and the corresponding pressure based on the Bernoulli's equation, and take that and use the pressure area method on the surface of the structure to calculate the wave load. And the advantage of this method is that it the most of the symmetric structures, many times we get the explicit expression for the wave load. On the other hand, this is Proud-Krylov theory. On the other hand, when the structural size d by lambda, that I will go to diffraction theory. In case of diffraction theory, what happens when m by d by lambda is greater than 0.2? That means, so what happens here? The wave that is impinged on the structure, I have a structure, when the wave impinges on the structure, what happens? It gets diffracted. Basically, the structure, there is a diffraction field is developed, because a part of the wave energy get reflected, it get diffracted, scattered, radiated out. So, the energy is diffracted and the diffraction field is developed, and in this case what happen, one has to apply, we apply the diffraction theory, and in the diffraction theory what we do, the total potential phi we call it as a incident phi I plus a phi s, that is the incident potential, is the scattered potential, plus phi r is called the radiated potential, and this is in for very few problems we can get a closed form solution, and otherwise we always go for numerical methods to obtain the solution of this. Once we know the diffracted potential, the total potential, numerical methods we apply, and once we get the total potential, then we always calculate the pressure by from Bernoulli's equation, and once we get the pressure from Bernoulli's equation, and once we get the pressure, then we calculate the force in a usual way by integrating. Again we can easily also calculate the moment, because once we know the pressure, we calculate the force and the moment on the structure, overturning moment, it can do that. But I will not go to details on this diffraction theory and Proud-Krylov theory, but I will just give in brief what happened to the Mauritian equation, and just because it is empirical formula, I will just briefly mention the Mauritian equation, the diffraction theory and the Proud-Krylov theory. It can be taken up in some other course because of the limitation of this, because this is an introductory course. So, I need not go to the details of this theory detail, there are other courses where it will be taken up. Now, if I go to the Mauritian equation, and this Mauritian equation, it was developed by Mauritian Brian, O'Brien, Johnson and Schaff. In fact, it was developed in 1950, and to evaluate the horizontal wave forces acting on a cylinder, vertical pile basically, and which is extended from the bottom till the free surface, still water level or the free surface. And as I have mentioned that here the total force, if I look at dF is the elementary force, it has two component, one is dFd plus dFi. So, this is the elementary drag force and this is the elementary total force, this is the elementary drag force, this is the elementary inertia force, and this is again given by the formula 1 by 2 CD rho d, d is the diameter, rho is the density of the fluid, and it is u into mod of u ds plus Cm into rho del u by del t into pi d square by 4 into ds. This is the formula. In fact, this is an empirical formula. And what happens, CD is the drag coefficient, CD is the drag coefficient, Cm is the ds is the elementary length of the structure, elementary length, for which the elementary force, elementary length of the cylinder. Basically, this we apply to cylinders, and then we have d is the diameter of the cylinder. Basically, this is suitable for pile type of structure because d by lambda is less than 0.2 and u is the velocity. What else? Rho is the fluid density. And the dm is the Cm is the ardent mass coefficient. A is the area of, this is pi d square by 4, it can be called as the area. Now, here we have a term modulus, because that will always, because the drag force and the direction of wave propagation, that will direction u is such that absolute value of u is taken, and because it is such that it is always in the direction of the propagation of the wave, that is why u is taken positive, because the drag force will retard this, whatever u will be, this will be always in the positive direction it has to take. So, this is basically the Mauritian equation, and Cm is sometimes called the inertia coefficient. We call this inertia coefficient. Now, if I know the elementary force dF, then what happen if I have a cylinder? If I have a cylinder, pile type of structure whose radius is d and its length is h, then what happen? What do we do? We calculate this total force F just by integrating over minus h to 0 dF. And that will give us basically integrate over minus, and here we have seen that only u and u is known, because for every eta, if I take eta is equal to a cos k x minus omega t, and this is integrated over the depth, the elementary force, because the ds is over the length, small elementary length, and minus h to 0 it is integrated. And here if I say that eta is a cos k x, this is a one of the wave elementary, basically one of the progress wave, then what is the corresponding phi? Always you know that this will be a g by omega cos hyperbolic k into h plus y by cos hyperbolic k h into sin k x minus omega t. And once we have this phi, then we get u just del phi by del x, that gives us the horizontal force. Once we have u, that is acting on the cylinder, once we have u substitute it in the Mauritian equation, the elementary force dF expression, and integrate it, and we get the force. In a similar manner, we can get the moment again by using the definition minus h to 0, h plus y, h is the length, h plus y into df, and that gives the overturning moment, In fact, large number of in a large number of observed structures, as I say that the piles are several piles are used. So, to calculate the loads on the piles and to calculate the moment on these structures, overturning moments on this structure, this Mauritian equation is used since 1950, and there are several other like one of the most important result in the water wave mechanics, particularly for the calculation of wave load on observed structures, and it is used to this equation, Mauritian equation is applied to a large class of problem for calculating the wave load on structures, even if mooring ropes and when mooring ropes and any structure which always we consider this as a thin structure, then wave load calculation, and where the structure is thin and where both inertia and viscous effects are very important, then always we apply this Mauritian equation to calculate the wave load on the structure, and it all depends, because once we have the empirical formula, we have empirical formula which depends on two factors C d and C m. So, depending on the nature of the structure, this C d and C m are calculated sometimes computationally, sometimes by model test or physical model testing. The C d and C m are calculated, and once C d and C m are known, which is always assumed that it can be found from various logbook, standard logbook. It has been mentioned for several structures, and in some other cases it is obtained by various model testing and from physical argument. And once this is known, then the CDCM, once it is known, then F and M are found, and that helps in calculating the wave load on the structure, particularly in case of Mauritian equation. On the other hand, in case of diffraction theory, particularly when the structures, because gravity platforms, when the structures becomes very large, we all depend on this diffraction theory, because here inertia force, here the viscous effects are neglected, particularly when we think of diffraction theory. The viscous effect is neglected, and we apply the potential flow theory. And in the diffraction theory, there are the small amplitude wave theory is the first order wave theory. What we have discussed in this course in the last several lectures, simple amplitude, our analysis is basically in the small amplitude wave theory, and which is often called the first order wave theory of Stokes. First order wave theory. On the other hand, there are higher order wave theories. Higher order wave theory, and particularly for wave load calculation on large structures, and these higher order wave theories are, this is basically comes from the Stokes finite amplitude wave theory, Stokes finite amplitude. Wave theory, because as I have told in the past lectures, I have told that what we are considering the linearized wave theory, and that is what the first order wave theory of Stokes or Ellis wave theory. But the higher order theories are obtained just by perturbing the nonlinear equations of the free surface condition and the other boundary conditions. And then the in fact, in observed mechanics, particularly for calculating wave load on structures, often we go to fifth order. Second order is large in the last 10 to 2 to 3 decades. Major emphasis was given on second order wave theory for wave load calculation on structures. Second order wave theory has been taken into account in the diffraction theory for wave load calculation, and even if there are cases here people have gone up to, scientists have or engineers have gone up to fifth order wave theory. Some of the details can be found, these wave theory details can be found in books on by offshore mechanics books or waves mechanics books in offshore mechanics or water wave mechanics. These details I did not go here because this course is an elementary course. Basically, I had tried to give a brief overview about various waves, various things about basics of waves, and then basic of wave load calculation, and the detail can be found in this. Apart from the linear theory, there are several non-linear theory, because unlike solitary wave theory, Contd wave theory, then we have solitary wave, Contd wave, and Stokes finite amplitude wave theory. Stokes finite amplitude wave theory, there we always go one by one, and the solitary wave theory, Contd wave theory, these are all basically nonlinear waves. Even if there is another wave which is called trochoidal wave. In fact, but for a large class of problem, these theories, there are a lot of results, but very few problems which are handled up now based on this theory when it comes to problems of practical nature. But major analysis, whether it is coastal engineering application, whether it is offshore engineering application, most of the time we always depends on the potential flow theory, and basically the viscous effect in potential wave theory, basically particularly the diffraction theory, the viscous effects are almost negligible, they are neglected because the structural size is always assumed to large. But this solitary wave theory or Contd wave theory, trochoidal wave theory, these are special type of waves, and sometimes nonlinear effects. Not much, several large number of academicians and scientists including mathematicians are involved in developing, trying to solve this class of problems, but because of the nonlinearity it is it has been difficult to handle the problem, the original problem. So, case to case problems are being analyzed, and several problems are attacked for solution as and when it is required based on model test or physical argument, and by generalizing, by simplifying the theory to as per the need of the requirement, as per the need rather I will say. So, this couple of lectures around, I think I have covered around 12 lectures on wave mechanics in this course, and further details can be found in other courses, but I will rather, my emphasis here was to teach the as an application of the basic potential flow theory, basic potential flow problems. I try to simulate, try to discuss this wave mechanics, and so that how one can get the wave energy, how one will go to calculate the surface elevation, wave load on a structure, and how the energy, in fact that is one of the major thing, how the energy is related. In fact, here we have two things, as I have mentioned, that our emphasis apart from the waves, because we have a fluid which is flowing and we have a wave which is propagating. So, here our major emphasis in the is the wave energy propagation rather than, and then there are two things which are, as we have seen that the particle motion, that is always related with the phi u, v, w, these may be the component, and then the acceleration. On the other hand, we have the phase velocity c, we have the group velocity c g. This talks about the energy propagation, and these things talks about the particle motion, group velocity, and this is very interesting that particularly there are two things here, there are two types of energy, one is the speed of the particle, one is the speed at which the wave energy propagate and speed at which the individual waves propagate. And then we have seen how the phenomena of what we studied in physics, various phenomena of reflection, scattering, transmission, radiation, all these things is arising in this class of problem. Diffraction. More on this diffraction theory or this radiation problems, this will be found in books on various application of these problems are there in coastal engineering application, coastal engineering, offshore engineering, and port or harbor engineering. So, here the emphasis is more. In fact, if you look at oceanographers, they may not be interested in waves of this wave, this type of, but when they, because their way of looking at problems is look at the whole, the domain is large. Here our domain for oceanographer, the domain is large. So, when they do wave modeling, they consider the wave modeling from a different perspective by assuming whole Indian Ocean or the Bay of Bengal as a single domain, and the grid size is different. But for coastal engineering or port and harbor engineering application, the grid sizes you always concentrate yours. The total area is a very locally, it's couple of kilometers or square kilometers area, but here they always there for them, maybe for oceanographers, maybe the one grid itself is 5 to 10 kilometer, but in the other hand for a coastal engineer or for any engineering activity, you always restricted to a particular location, but here they look at the whole ocean as a whole, as one domain. So, because of that, the analysis point of view, because we, our potential flow theory is good enough to analyze the flow problems here for most of the activities, developmental activities related to engineering. However, many times the information study on oceanographic data that is required, because what exactly happen at various parts of the ocean, how the wave nature changes, how the topography affect the things, these information are collected from the ocean, and how the ocean circulation modeling, all these informations sometimes are required for any kind of activity, and developmental activity takes place after getting the data from oceanographer and analyzing locally by a ocean engineer or a professional engineer who does lot of analysis and computation on this class of problem by doing physical modeling or numerical modeling, and then coming out with fruitful solution to for the designer to design various structures or various developmental for which are used for various developmental activities. And this is this few lectures are in fact it is very briefly discussed about the basics of waves, and however more about waves one can find, because today there are several books on wave mechanics, water mechanics, and various aspect of coastal engineering, port and harbor engineering or ocean engineering are dealt with in a different manner. So, depending on the requirement, one will always choose the problem and analyze these things. Another aspect of today's concern is the energy extraction from the ocean waves, and that is wave energy extraction, renewable energy. Renewable energy, and we all say that ocean is a, and we have seen that in case of wave E is rho g h square by 8, and this gives us, if wave height, from wave height it is the square, energy is proportional to E varies as a square, but one of the today's one of the difficult problem is how to extract the waves, and lot of there are lot of efforts are made, but significant progress has not yet have not yet arrived with a significant progress. There is not much is done in this aspect when it comes to extraction of the wave energy, basically from tidal waves or even further. And there are other aspect, I think I have particularly the understandings are not clear on the breaking, wave breaking. And as we have seen that the like as I have wave breaking is a phenomenon where this happens more on the near surf zone area, particularly in the coastal areas, because that larger waves often, as I have mentioned, that larger waves often we reduce it to smaller waves by breaking them. And but what happen, how the mechanism of breaking takes place, it is still a lot more theoretical progress is not much. Various model testing people are doing, but to understand the concept, but theoretically not much progress is done on this aspect. And another few things in so this is all goes beyond the limits of this course. So, I am not going to the details about this wave breaking or energy extraction, renewable energy or various application of wave mechanics, basically in the areas of coastal engineering, port and harbor engineering, and even if naval architects, they need lot of, because when you go to wave load calculation, particularly if you are interested in the wave resistance test, particularly knowing the how much resistance the wave provides when a ship moves, or so it is required in the design process, and these are the details which goes to the application side. On the other hand, for a subject, theoretical subject like for a physicist or a mathematician, it is more challenging also, because there are many things, even if in the potential flow regime, because of the nonlinearity of the problem, lot of mathematical challenges are there in this study of wave mechanics, particularly marine hydrodynamics, the branch of marine hydrodynamics. And on the other hand, today I will conclude this part of the lecture, that is on waves, and then in the next couple of lectures we will just introduce, I will try to introduce to you about the viscous flow, viscous effect, and a brief about these things. We will talk in brief, because this course has major emphasis on emphasis given on potential flow and its application basically on wave mechanics, and just a glance we will go to the boundary layer theory, laminar boundary layer theory. When we talk about viscous effect, basically we have talked about equation of motion. When we have talked about equation of motion, we have assumed that the viscosity, intermolecular force of attraction we have neglected, and in the process we have assumed the flow as envisioned. There are a lot of challenges in problems associated, as we have seen, lot of challenging mathematical problems are there, and associated with the envisioned fluid, but we will still briefly discuss about viscous fluid in the context of this series of lectures on marine hydrodynamics. Of course, fluid mechanics in general or with viscosity, these are different other courses, but here I will just give a brief introduction to viscous fluid. And some of the flow characteristics, and simple, try to work out few simple problem to have a basic understanding about the Navier-Stokes equation and its application. Basically, we will concentrate on Navier-Stokes equation. This requires a full-fledged course, but I will just briefly mention without going to the detailed derivation of the Navier-Stokes equation, and then I will work out few problems after completing a series of lectures on this. Then I will talk in brief, I will discuss about boundary layer theory, and then we will conclude this series of lectures with this today. For the details we will discuss later, and today we will stop here. Thank you.